the interaction of light with matter has been essentially my main area of concern and research over the last 20 or so years after I immigrated from France to New Zealand. And essentially, I'm going to tell you very briefly about it. So light is really everywhere. Sometimes we forget about it. I mean, if there was no light, this presentation would be very boring. It underpins all of life, sorry, and a lot of our technology. I mean, the internet is just powered by light traveling around the world in glass tubes. There's also a lot of light in popular culture, and some of you might remember this New Zealand flag with the laser kiwi from a few years back. When you work in science, in general, typically you interact with light through spectroscopy, which is essentially how you analyze light to understand its properties, but mostly how it will interact with materials. And you must be familiar with some of those aspects of spectroscopy. Spectroscopy is about understanding the spectral component of light, colors, and you can do that using a droplet of water. You can do that using a prism. In practice, most spectrometers nowadays use a diffraction grating, and it's essentially a glorified version of this, a lot of lines that are very closely tied to each other. The light diffracts through that, and if you've got some optical elements, you can then use a sensor, which is typically similar to the sensor you have in your camera, phone camera, and by looking at what's coming to the sensor, you can separate the component of light. So typically, broadband light, like these light sources, would have a very broad spectrum. And more recently, 60 years ago, the advent of the laser really transformed the way we do spectroscopy. So the laser, typically, we think of it as something that has a very sharp spectral component, like very well-defined color. It has other properties, and one of the properties that's not always obvious is that you can really condense it, focus it to very, very small areas. So you can do spectroscopy at the micrometer scale with lasers, which would be very difficult with normal light. So it's really a magic tool that is used across all science. This is an example of laser spectroscopy, fluorescence spectroscopy. It's a very common one. I use it for demo when you go to schools. I take a bottle of this, of tonic water. It contains the quinine, this molecule, which is a fluorescent molecule. So when you shine a purple laser through the quinine, you can see the laser line here. It emits blue light. So as it goes through the tonic, you see some very bright blue light emitted. Fluorescence is the workhorse of a lot of scientific area. You've seen already images from previous talks, but in biology it's used all the time as a stain, is a way to image cells at the micrometer scale. So very efficient, but it doesn't give you a true chemical identification. You see colors, you've tagged your things, and you can tag certain genes and things like that, but it's not really a true chemical method. What we've been working on a lot is another type of spectroscopy that tries to detect how light interacts with these molecular vibrations. So at the molecular level, those molecules are never static. There's a lot of way they interact, they vibrate naturally, and light can interact with the energy of these vibrations. This type of spectroscopy has almost, well, it's coming to 100 years. It was discovered or invented in India by an Indian scientist, and it's called Raman spectroscopy. And the beauty of this method is that it gives you a fingerprint. All these peaks here correspond to one vibration of the molecule, and with some proper analysis, it's essentially a fingerprint of your molecules. You can clearly identify whether you've got cocaine or paracetamol, for example, in something like that. It's not perfect because it's a weak effect. It doesn't really work like fluorescence, so you need a lot of the material. You need some very pure substance before you can really say something accurately and detect. So our work has been trying to use new technology. I mean, sorry, I forgot about this. This is actually used just not by us, but it's found its way to some remarkable application. Like, for example, this was an example a few years back where Raman spectroscopy used to give direct feedback to the surgeon when during the operation to see whether some parts were cancerous or not. So it's found its way to a lot of applications. But in principle, we could widen the range of application if we could improve its sensitivity. So that's where the nanoparticles come in. We've worked a lot with metallic nanoparticles in particular, and over the last 20, 30 years, there's been a lot of progress on how you make these, how you characterize these with electron microscopy. And the beauty of those metals, like silver and gold, is that they interact strongly with light. And when you have nanoparticles, they interact with visible light. And you can really see that by changing the shape, the size of those particles, you actually change the color and how they interact with this. If you use them in the right way, you can channel all that light and try to use it essentially as lenses to try and focus the light to very small areas. And that was the principle of the work we did in terms of single molecule detection. We use what's called surface enhanced Raman spectroscopy. These are images of the lab that we use. So we have different lasers, and it's just a bigger version of what the surgeon was using in the previous image. And this is the sort of experiments we were doing. We had these nanoparticles. We had molecules that are located typically just at the junction between two nanoparticles. And when they are illuminated with light at a certain wavelength, you can measure their Raman spectrum. And we were able to show that under the right conditions, you could actually detect just one molecule, the one that was right in the middle. And the enhancements we're seeing are huge, like it's of the order of 10 to the 10 billion times larger. And we spent a lot of time with Pablo Echegonin and my current colleague, Baptiste Augier at VEC, to try and understand the fundamentals of this method. Now, in the process, unfortunately, this has not yet found really some application. It's remarkable that we can detect this one molecule, and it's fantastic for fundamental studies because you can look at what one molecule does compared to 10,000 molecules. But it's been hard to do in a reproducible way, in a way to really detect, trace amount of molecules. So, but in the process, what we did is we actually, maybe 10 years ago with one of my students, we were developing new methods to understand those nanoparticles, those metallic nanoparticles. And one of those new methods involves, well, we can't see it here, but a new type of optical element called an integrating sphere. And it allowed us to look at those metal nanoparticles with a bit more accuracy than standard methods, if you want, or we were able to detect some properties of them that were not easily detectable. And we started a company because we thought this thing can have applications in many areas. Essentially, our method allows to do spectroscopy with substances that tends to be dirty or scattering. And we started to develop this instrument that we're now building in Wellington. We've built about 100 of them so far. And we originally sold them to the wine industry as a way of monitoring what was happening during their process, because it's it's a dirty environment. But over the last 1 or 2 years, we've moved now to selling this to this market, this mRNA lipid nanoparticles. So this is the technology that underpins those COVID vaccines, and that apparently will really be the next generation medicine, personalized medicine, and so on. So these RNA can do a lot of things in terms of therapies, but they can't be injected directly in the body. They need to be protected by some vector, typically this essentially a ball of fat that protects the RNA to inject it, and so that it can target the right part of your body. This is the subject of a lot of research at the moment, and as a physicist, some of it is really not my expertise, but I'm getting more and more into it. But it just happens that our instrument was the perfect instrument for this thing, because normally, when you measure RNA, you would use this sort of optical spectroscopy, and you get a measurement, a quick measurement of the concentration. But those nanoparticles interfere with the measurement. You can see here they create this white background that prevents you from measuring RNA accurately. And our instrument was precisely designed to remove that background. So now we actually have a company. We have about 20 people in Wellington building this and selling it mostly to the US and Europe, but to the biggest pharma company trying to use it for this sort of application. So yeah, that's the story from really fundamental research. We had a few Marsden grants that helped along the way, and that essentially triggered this move to commercialization, where I am spend essentially a lot of my time now. Yeah. Thank you.